One.
All right. Welcome, everybody, to another meeting of the Warren Astronomical Society. I'd like to thank you all for joining us on a Thursday night on what would ordinary times have been our Macomb meeting. Because of the restrictions of our dual interface, where we've got some people live on WebEx and some people watching via YouTube, we, of course, are not going to do the normal roll call. However, I understand we have a special guest tonight who's going to be introduced to us by Ken Burton. Ken, I think you have something very important to say to the gang.
I want to introduce to you David Levy. You probably see him on your screen. David is famous for comet finding. He's out in Arizona right now. He and I share a very common friend, in L.A. Mayor, who actually spoke before us a number of years ago. David is joining us. That's the Shoemaker Levy 9, wasn't it 9, right?
Yes, exactly.
It went right into Jupiter and changed the spots, as they say. This is David Levy. If you want to say a couple of words to the group, we would love to hear from you.
Indeed.
Well, thank you. And it's really a pleasure to be here. I was actually looking for groups that I know that are having online meetings now during this pandemic shutdown. And I found the lovely Warren Astronomical Society. And it's a real pleasure to be here. And I hope to be a regular appearance on your Thursday night meetings. And thank you very much. And I'm going to hand it back to you guys now. And I'm looking forward to this meeting as much as the rest of you are.
Thank you so much. It's an honor. And I do believe, though it was a little before my time when the telescope was built, that we have your own autograph on the jewel of our telescope collection, the Frank McCullough reflector. Isn't that right, Jonathan?
That's correct.
Yep.
Fabulous. So nice to have you touch base with us again. It is indeed an honor. All right.
It's a pleasure for me.
Thank you. And let Mr. Mayor know that Jonathan and I love his book on Venus. Very good. Okay, so we are going to kick things off with In the News in the Sky, as presented to us by Kenneth Burton. And then we will segue into officer reports, special interest group reports, observing, and then follow it with our informal snack break before we get into the main feature of the night. So Ken, if you don't mind, take it away.
Okay, give me a second here while I get myself situated here.
I muted everyone else, so you'll just hear Ken.
Okay, here we go. This is In the News for 5/20/2020. There are several items. We also have In the Sky tonight, which is gives us a little bit of an idea of what to look for in the sky. And this is and here we go. Here we go. Well, telescopes and spacecraft join forces to probe.
I think.
Oh no! I think we lost.
Yeah, we've lost his audio feed. I see circling going.
I do too.
That always happens. There isn't much we can do. By the way, Diane, hi, it's Adrian.
Hey, good to see you again.
We lost him, but we got a beautiful picture of Jupiter.
All right, Ken is back. All right, I'm muting everyone again.
David.
Are we okay? Where are we?
Yes.
Yeah, we're back.
You're back.
Okay.
We lost you almost as soon as you started, so get back in.
Let's do it again. Here we go. This is a report from May 7th, 2020. Telescopes and spacecraft join forces to probe deep into Jupiter's atmosphere. This is from the NASA Goddard Space Flight Center. The summary says that the NASA's Hubble Space Telescope and ground-based Gemini Observatory in Hawaii have teamed up with the Juno spacecraft to probe the mightiest storms in the solar system taking place more than 500 million miles away on the giant planet Jupiter. The team of researchers is led by Michael Wong of the University of California, Berkeley, Amy Simon of NASA's Goddard Space Flight Center in Greenbelt, and Imke de Pater at the University of California, Berkeley, are combining multi-wavelength observations with Hubble and Gemini with close-up views from the Juno's orbit about the planet, gaining new sights into the turbulent weather on this distant world. We know how Jupiter's atmosphere works, one said. The constant storms are gigantic compared to those on the Earth, with thunderheads reaching 40 miles from top to bottom, 5 times taller than typical thunderheads on the Earth, and powerful lightning flashes up to 3 times more energetic with the Earth's superbolts. Another report. This is a May 6th report, day before. The ESO instrument finds the closest black hole to Earth. Invisible object has 2 companion stars visible to the naked eye. May 6th report from the ESO. Astronomers have discovered a black hole lying just 1,000 light years from the Earth. The black hole is closer to our solar system than any other found to date and forms part of a triple system that can be seen with the naked eye. The team of astronomers from the European Southern Observatory and other institutes have discovered this black hole, again lying for 1,000 light years from us. We are totally surprised when we realize that this is the first stellar system with a black hole that can be seen with the unaided eye. Emeritus scientists of the Academy of Sciences and the Czech Republic in Prague and co-authored the research, Peter Hadreva, said. Located in the constellation of Telescopion, the system is so close to us that its stars can be viewed from the southern hemisphere on a dark, clear night without binoculars or telescope. The system contains the nearest black hole, as we said. The team originally observed the system called HR 6819 as part of a study of double star systems. Powerful new AI technique classifies galaxies in astronomy image data. This is a 12th of May 2020 report from the University of California at Santa Cruz. Researchers have developed a powerful new computer program called Morpheus that can analyze astronomical image data pixel by pixel to identify and classify all the galaxies and stars in large data sets from astronomy surveys. Morpheus is a deep learning framework that incorporates a variety of artificial intelligence technologies developed for applications such as image and speech recognition. There are some things we cannot do as humans, so we have to find ways to use computers to deal with the huge amount of data that will be coming in over the next few years from large astronomical survey projects, said by researcher Brant Robertson. We have a breakthrough study of perplexing stellar pulsations. Astronomers have detected, this is a May 13th report from the Goddard Space Flight Center. Astronomers have detected elusive pulsation patterns in dozens of young, rapid rotating stars, thanks to data from the NASA's Transiting Exoplanet Survey satellite tests. The discovery will revolutionize scientists' ability to study details like the ages, sizes, and compositions of these stars, all members of class named for the prototype bright star Delta Scuti. Delta Scuti stars nearly pulsate in interesting ways, but the patterns of those pulsations have so far defied understanding, said Tim Betting, the professor of astronomy at the University of Sydney. To use the musical analogy, many stars pulsate among simple chords, but Delta Scuti stars are complex with notes that seem to be jumbled. Tests have shown us that's not true for all of them. The paper described the findings, appears in the May 14th issue of journal Nature. There's a new comet discovered by the Solar Observatory May 13th by the NASA Goddard Space Center. In late May and early June, Earthlings may get the glimpse of Comet Swan. The comet is currently faintly visible to the unaided eye in the southern hemisphere just before sunrise. The new comet was first spotted in April of 2020 by an amateur astronomer named Michael Matazzo, using data from the SOHO satellite, which you can see there. The new comet was first spotted by this amateur astronomer using the SOHO instruments in solar wind anisotrophies, or SWAN, as seen here. By the way, the comet also appears to leave the left side of the image and reappear on the right side around May 3rd. You can see that they were able to use this, and because of the SWAN's 360-degree all-sky maps are shown, much of the globe is represented by a two-dimensional map. Transit 1, planetary orbits are not misaligned. First scientific result by the new spectrograph on the Subaru telescope. This is a May 14th report from the National Institute of Natural Sciences. Astronomers have determined that the Earth-like planets of TRAPPIST-1 system are not significantly misaligned with the rotation of the star. This is an important result for understanding the evolution of planetary systems around very low-mass stars in general, and particularly the history of TRAPPIST-1 planets, including the ones near the habitable zone. ESO telescopes see signs of planet birth. This is the twist. The twist marks the spot, as they said. This is a source of the ESO. Observations made by the European Southern Observatory Very Large Telescope have revealed the telltale signs of a star system being born. Around the young star AB Aurigae lies a dense disk of dust and gas in which astronomers have spotted a prominent spiral structure with a twist that marks the site where the planets may be forming. The observed feature could be the first direct evidence of baby planets coming into existence. Thousands of exoplanets have been identified so far, but little is known of how they form, said Anthony Bacaletti, who led the study from the observatory in Paris. Astronomers know planets are born in dusty disks surrounding young stars, like AB Aurigae, as cold gas and dust clump together. The new observations for ESO's VLT, published in Astronomy and Astrophysics, provide crucial clues to help scientists better understand the process. Let's see. The next story is about Alma, who discovers massive rotating disk in the early universe. This is a May 20th report, National Radio Astronomy Observatory. In our 13.8 billion-year-old universe, most galaxies, like our Milky Way, form gradually, reaching their large mass relatively late. But a new discovery made with the Alma Large Submillimeter Array, ALMA, of a massive rotating disk galaxy seen when the universe was only 10% of its current age, challenges the traditional models of galaxy formation. This DLA0817G, nicknamed Wolf Disk, after the late astronomer Arthur M. Wolf, is the most distant rotating disk galaxy ever observed. The unparalleled power of Alma made it possible to see this galaxy spinning at 170 miles per second, similar to our Milky Way. While previous studies hinted at the existence of these early rotating gas-rich galaxies, thanks to Alma, we now have an unambiguous evidence that they occur as early as 1.5 billion years after the Big Bang, that said lead author Marcel Neilman of Max Planck Institute of Astronomy in Heidelberg, Germany. There's also another couple of, those were artists summative. These are by the Hubble and Alma, and by the Very Large Telescope of actual pictures of it. And that is in the news for 5/20/2020. Let's move on to In the Sky. This is In the Sky for May 20th to June 1st, 2020. What is that? Mercury and Venus will pair up in the west after sunset, their closest pairing of all of 2020 on May 21st and 22nd. These two worlds will pass within 1 degree on the sky's dome. That's approximately the wrist of a little finger on your arm's length. Their pairing takes place low in the western twilight sky. Bright twilight will make Mercury hard to see, but Venus is very bright. Its brightness will pierce the twilight, making Venus an interesting and beautiful object to see now. Plus, Venus can help you find and identify Mercury. Did that come in? Yes, good. The young moon and Venus and Mercury on May the 23rd and 24th will show up as well, 45 minutes after sunset. Darkness falls on May the 26th, 2020. The moon lodges in front of the constellation Gemini, the twins. and the lit side of the waxing crescent moon points right at the planet Mercury. The moon and the Gemini stars Castor and Pollux should be fairly easy to see tonight as they stay out past nightfall. On June 1st and 2nd, 2020, use the waxing gibbous moon to find Spica, or Spica if you like. Some like Spica, some like Spica. I always thought it was Spica. Anyway, the brightest star in the constellation of Virgo the Maiden. In fact, Spica is Virgo's one and only first magnitude star. Although the bright moon will wipe out the number of fainter stars from the canopy of the night, bright Spica should withstand the moonlight's glare. If you have trouble seeing Spica, place your finger over the moon and look for the bright star nearby. And that is in the sky and in the news for May 20th to June 1st, 2020. Any questions? We're good. Thank you very much.
Fabulous. Thank you, Ken. And it is all right. Okay, thank you.
Because you have to have an active mic, and they've muted us.
Yes, please, if there's no questions for Ken, please mute your mics so that we can do the officer reports without any feedback. Thank you. All right. So, again, thank you all for continuing to participate in the Warren Astronomical Society in our current online-only phase. It's been great to have the attendance that we've had at our meetings as we've continued to bring you our original content every couple of weeks, just as normal. And I think that the online open houses have been fun. The officers, of course, have been working in conjunction with various institutions that host us to see when things will be safe to resume, and not before then. We've been abreast of things like concerning stories of the possibility that COVID-19 can be transmitted through the eyes, which seems less of a possibility, more of a, yeah, that is something that happens, which of course has implications for star parties and any sort of communal observing. So we're working with Macomb Community College, Cranbrook, the Metro Parks, etc., to make sure that when we do resume, it will be safe. And in the meantime, I think we are all having a pretty good time from our homes. We've got Dr. Dale Parton, our program chair, has a nice slate of speakers coming up for June. June 1st, Alan Kaplan will give the feature presentation on space medicine, while Treasurer Mark Jacobison will give a short talk on astronomical seeing. Then on June 18th, Mark O'Malley is going to clue us into the life and times of Werner von Braun. Whether or not we'll get to hear the Tom Lehrer song is yet to be determined, but I love that song. All right. Our second vice president, Riyad Mahdi, is the observatory chair. Of course, we have not been able to go to Stargate, but Riyad has been keeping an eye on the place and keeping in contact with the metro parks. So we know that the observatory is secure and in good shape, especially given all the extreme weather we have had. Our treasurer, Mark Jacobison, has his most recent set of minutes published in the WASP. Our secretary, Glenn, has been writing the minutes, which can also be found in the WASP. Our outreach director, Bob Tremblay, has had a much lighter calendar in his second year of this current term than he did last year, because at present we are suspending all in-person events. We did have talked about jumping on to certain virtual events. We're trying to work out the feasibility of how we would do that other than the virtual open houses that we've already been bringing you. And we've got publications. Jonathan Cade is our publications director, who is always on the hunt for new articles and new forms of content. The WASP is out. The next one will be coming out shortly because June 1st is a Monday. So if you have anything to send to Jonathan or WASP editor Dale Teamy, try to get it written Memorial Day so you can get it in before next weekend, because we will want it coming out on time. As far as our subgroups go, Solar Marty reported to me last night that in his capacity as captain of the solar group, that sunspot activity has of course been low. There have been prominences noted and reports in the bad form of the media that the solar minimum is going to lead to mass starvation. Yeah, please don't lose sleep over that. We've got enough to worry about. Publication History SIG chairman Dale Teamy has scanned in more copies of the vintage Detroit Astronomical Newsletter Society that we're lucky enough to come across. So those are online. He wanted to highlight the February to March issue of 1981's W.A.S. newsletter. They were proposing to assign a club historian. Dale wonders, 39 years later, how that one went. Also in 1981, he would like to know you could get a copy of the Observer's Handbook, the famous Rask Observing Handbook, for all of $6 American. So yeah, those are the days. And discussion group chairman Jeff McLeod will resume in-person discussion when it is feasible. Bill Beers, our astrophotography chairman, is he on the line? I do believe he is. Bill, I know you've been out and about your place up north. Have you got anything for us?
Yes, I do. First of all, I'd like to do a shout out to David Levy. Welcome to the Warren Astronomical Society. I remember meeting you at the Great Lakes Stargaze years back, so that was fun, and you had a great talk going on there. But anyway, what I'm going to try to do is share my screen here. Can everybody see my screen?
Yep.
Okay. All right.
Yes, we can.
Okay, what I've been doing, a week ago, we were talking about the supernova. A week ago, I shot this. This is Messier 61 with supernova 2020 JFO in it. Now, John, you were talking about looking at it through a telescope. Well, you can see the 4 stars that you were probably looking at. But what I found interesting about this, and the reason I wanted to show it, is because when you zoom in, what I discovered is the supernova had a blue tint when I saturated it. So, why is it a blue tint supernova? Talking to Gary Ross had a good explanation that I caught it just before the peak intensity. So that might be typical of that. Now, another friend sent me some information on this, and they claim the reason the supernovas are blue is because they're very, very old. They're like first generation stars. So with that said, Messier 61 Galaxy is 13.2 billion years old, which means that star could have been a very first generation star in that galaxy. And it just exploded back on May 6th when we first saw it. So for the new astronomers out there, to give you an idea how far away things are, like I said, Messier 61 is 53 million light years away. So when that exploded just right after the dinosaurs were becoming extinct. And we're just now seeing the light from that supernova. But I thought it very interesting why it had the blue tint to it, and it'll be real interesting. Like maybe Doug will do another image of it later, a little while from now, and see if it's still blue color. So that would explain the correct phase of capturing it. So I just thought I'd throw that out, especially for the new astronomers who aren't familiar with sizes and distances of all this stuff that we look at. So, and if anybody has any questions about astrophotography, feel free, you can get a hold of me anytime.
All right. Thank you so much, Bill. Okay. So that wraps up our officer and subgroup captain reports. We have some time for observing reports. I do think we've had a few favorable nights wherein people got a chance to observe, and I know at least one member who did some nice deep sky observing over the last weekend. He's smiling. Come on, Jonathan, what'd you see?
So I made my trip up to our dark sky observing site in Black River, Michigan, last weekend, and I managed to make it up and back down to Oscoda on one tank of gas. I only stopped once for gas and once to use the facilities, and otherwise didn't encounter any human beings. So I thought it was pretty successful in maintaining physical distancing. So I along with my observing companions, who I named Procyon and Pouchy, Procyon being the genus of the raccoon, and Pouchy being America's favorite marsupial, the opossum. We did some quality observing of the galaxies in Virgo, Coma, Leo, and then a lot of galaxies around Ursa Major and Canes Venatici. And I spent about an hour and a half, maybe 2 hours, looking at just M61 on 2 different nights. I want to believe that I observed the supernova visually, but I was only using a 10-inch. They are the best skies in the lower peninsula, so if you can see it with a 10-inch, I probably did, but I can't claim it for certain. But I did just have a great time with M109, M106, of course M51, and some of the other brighter ones. But it was just it was supposed to be rainy all weekend, which is one of the reasons that Diane didn't come with me. But it ended up being 2 clear nights. So it just goes to show my best observing advice for people in Michigan is go where the skies are dark and hope that the weather cooperates, because you really just can't tell what's going to happen with the weather here. So
Yeah, I got to see an ISS pass that night. Can't see much else from Dearborn, other than Venus.
yeah, we actually were looking at the same ISS pass together. It was very romantic.
Yeah, it was. So then, who else has got an observing report? I hope to have some next time after I get up to see the same skies Jonathan was appreciating. But I'm sure somebody else out there, besides Jonathan and Bill, have had a chance to take in some dark skies somewhere.
So
Or see Venus. Yes, Adrian, I see your hand.
Doug Bach kind of knows this well, because I was explaining to some folks here. I got a chance to go to Hudson last night. Early this morning, there was a bank of clouds that obscured Hudson all up until about 1:30 or so, which was when the galactic center rises. So it's kind of the first glimpse of the galactic center. So I was there taking pictures with a camera mount between 1:30, and by the time it clouded over again, it was around 4 in the morning, and I had to work this morning. So, but the skies opened up. They looked beautiful. I took a few pictures, and unfortunately, I didn't prepare to show any of them here in this forum, but I did get a few of them. Doug, whose thunder I'm stealing, had some supernova pictures. He did some work, and I was, while heading to Lake Hudson, I was listening in to his stream. So it was a good night. It's as if the skies cleared in just enough time for me to do some work with this new mount that I had, and it did a great job. I need to polar align a little bit better with it, but I got some pretty deep Milky Way shots. So I was very pleased.
That's great. Thank you for sharing with us.
No
Who
problem.
else? These are hard to top.
David's
So
ready.
on the on the YouTube stream, we have a viewer whose username is Erpagris1. I'm not sure what that stands for. Who said that they saw Venus and Mercury at sunset last night in Cairo.
Nice.
So make sure to. This is a great opportunity to see Venus getting closer and closer to Mercury, and of course Venus is a thinner and thinner and thinner crescent every night. So keep watching it. Don't miss the opportunity to see it, because there's nothing else in the solar system that gives you a show like a thin Venus crescent. It can almost look like a full circle. So
Yes.
just keep looking, but
And
safely. Always make sure the sun is blocked when you get your binoculars out.
David has something apparently.
Yes, that's what I just read. Yes, David, please.
Is that me?
If you had your hand up.
Yes, I did have my hand up. I just wanted to say that last night while searching for comets, I picked up a bright meteor waltzing its way through Ursa Major. It's either a Chi Scorpiid or a Tau Herculid. Both of these meteors are very slow. They really don't fall. They kind of waltz their way through the constellations. It lasted for about 6 seconds. It was really pretty interesting to say. And usually when I say something to a group like this, I usually end with a little poem. And Robert Frost wrote one of my favorite poems, The Road Not Taken. I shall be telling this with a sigh, somewhere ages and ages hence. 2 roads diverged in a wood, and I took the one less traveled by, saw the meteor, and that has made all the difference.
Lovely. Yes.
I have something real quick. One of the viewers wanted to know my email address to get a hold of me.
All right, and we can see it right side up and right ways forward.
Is that right side up?
Yes, BEEZOLL@AOL.com.
Right.
Those
I
of
don't
you
know
playing
who that
along at
person
home.
was, but that's my email address for any astrophotography questions.
Thank you. Thank you. All right, we are a little bit ahead of schedule, so we do have time for Ask an Astronomy Question. And somehow I get the feeling that with the crowd we've got tonight, any question under the sun will get an answer. So,
Although we don't guarantee it's correct.
Yeah, well, we never guarantee it's correct.
Diane?
Yes.
This is Jim.
Hi, Jim.
Dale and I were exchanging emails here recently about the July debate that was supposed to happen.
Yes.
And we thought that it might be appropriate. I suggested that I thought it would be very difficult to do it under the situation that we have, that Dave that Dave would, or Bill wouldn't be here, and Dave would not be able to do it with a Zoom thing, but over the telephone. So we thought we might want to talk about it here and see if we should either delay it until such time as we can meet in real life, or find a substitute for it or something of that nature.
Yeah, absolutely. You can hash that out during the snack break. No problem. I mean, we understand that.
We just thought that it might be somebody else might have ideas. So whatever.
No, I mean that's fine. I completely understand a debate. Debate works a lot better face to face with a live audience anyway.
Right.
Yeah.
Lose is a great deal.
Indeed. And then we wouldn't be able to.
Especially we wouldn't have John Blum and a referee. Uniform, so.
Or the participants pretending to do
Yes, I
fisticuffs.
certainly insist on being the referee if we have another debate. I've still got my referee shirt that I bought special for this debate.
Okay.
Lovely. Thank you, John. All right. Any questions?
Somebody must have some astronomy question out there. Anybody? There's no stupid questions. So if there's anything you wanted to know about astronomy, if you're new, feel free.
All right.
So
I've got a question.
Okay, Jim.
Go ahead.
Can someone explain in common English how we determine the age of the universe by looking at the cosmic background radiation?
That's
We
a
have
good question.
several people that's right up their alley. Who wants to take that one? A Dale or a David or a Dave? I think several people quite like that field.
And motions of the galaxies,
There's a big debate going on now about the age of the universe because of the
Hey, that's done.
incompatibility of the Hubble constant measurement, and it's got to do with the cosmic background radiation versus actual observations of supernova 1As and stuff like that. So,
all right, there you go.
okay,
I'll make some comments about it.
Go for it.
People who model the Big Bang would say that at a certain stage, it was so hot, and all hydrogen and helium were ionized. And that meant it was a plasma and it was opaque. But when it got down to a temperature of, if I remember right, about 3,000 degrees Kelvin, the electrons were able to bond to their nuclei. And
Right.
so the universe fairly abruptly became transparent. And whatever temperature existed at that time meant that there had been a black body radiation curve, meaning a distribution of energy at different wavelengths that was peaked at a certain wavelength characteristic of...
Plain English enough. Oh, it's extremely plain. So you
We're picking up somebody else's...
That was the Ross household. I muted them again. I don't know that they knew they were on a live mic.
Well, anyhow, so at a characteristic of 3,000 degrees Kelvin, the universe became transparent.
Right.
And so wavelength peaking at a temperature characteristic of 3,000 Kelvin was pervasive in the universe throughout it. As the universe continued to expand, it cooled. And when you expand, it stretches out the wavelength of the dominant light, characteristic of 3,000 Kelvin. It has since expanded by a factor of over 1,000. So the wavelengths characteristic of 3,000 Kelvin have stretched now to about 3 degrees Kelvin. That's what we're seeing. We're seeing that flash of the Big Bang stretched out into the microwave region. And by the ratio of the peak and wavelength of that wavelength now to what it was at 3,000 Kelvin, you can calculate the age of the universe. That's sketchy, but it's... Yes?
There's one thought that I've heard more recently that they missed the boat a little bit on the expansion of the universe itself, saying that it's expanding a lot faster than they thought that it is. And does anybody have any information as to whether that 13.8 billion year life is actually accurate? It's expanding ever increasingly. It may be, somewhere between a billion years or 1.5 billion years younger than the 13.8 that it was given.
we will be talking about that in September, if that makes any sense for you.
Okay, great.
And thank you, Dale, for you just kind of confirmed what I thought was the answer, except that again, you're suggesting we are projecting the age of the universe from the very, very, very carefully measured.
Hey, Dave, I'm going to try to see if I can combine a call with you because we are getting to very close to... Yeah. And
Yeah.
Sorry.
Carry on, Jim.
Well, I'm just saying we very, very carefully measured the redshifted CMB radiation from the 3,000 degrees that you mentioned earlier down to I believe it's 2.700.000. And we're suggesting that the radiation, the redshift, will give us an age of the universe from for that shift to going from, you said approximately 1,000. I believe it's just over that. But so I was just wondering whether there was another mechanism that is used to project the age from the CMBR. So,
well, look, there is a problem in that getting the age of the universe and its expansion rate from looking at certain types of supernovas is showing that there's a discrepancy.
That's right.
I forget how big it is. At most, it's around a 10% discrepancy. And my comment to that is, that's great. Astronomers, professional astronomers love that kind of thing because there's something going on that we don't understand to be explored.
Right. And that's kind of the current crisis in cosmology thing going on right now. So thank you.
I wouldn't call it a crisis. I would call it dessert.
Yeah. Yeah. There's always another avenue to explore. Okay. So that takes us basically to break time, our 15-minute break. I just do want to mention that our former president, Jeff McLeod, is currently doing bi-weekly live streams on astronomy issues. It's called Jeff's Astro Chat. It's available on Facebook, and you can check out his prior episodes, which I find quite entertaining. And if you've got some interesting questions that you'd like somebody who's currently doing an astrophysics degree to expound upon at length, that's a great way to get an hour-long deep dive into your questions. So that's an avenue too. All right, so just do mute your mics if you're going to be enjoying any food or drink, but we're going to take a little brief bio/snack break. Sorry we can't provide the refreshments. Jonathan and I have been eating them all since we bought a whole box of chips back in Cheez-Its back in early March. And we'll see you at 8:30 for the feature presentation.
Say, Dale?
Yeah.
Another little bit of discussion again about the debate. If and I don't know if we'll get to include Dave into the argument or to the discussion, but if you need to, this was going to take the place of the presentation at the July meeting. Was that the plan?
Yes.
I could, if you need to, I could conjure up a presentation I gave about 10 years ago. It's kind of the prologue to my September presentation. I don't know if you recall. It was called the Way We Found the Universe. It's about the Hubble, the Hubble, Einstein, Lemaitre. The great debate of 1920, Hubble's discovery of the Andromeda Nebula, or the Andromeda Cepheid, and then his further, in 1929, his further expose of the expansion of the universe, and Lemaitre's countering Einstein's theory, cosmological constant, so on and so forth. That was called, it was based on a book by Marcia Bartusiak called The Day We Found the Universe. And I gave it to the club, I think in 2009, I believe. So if we don't do the debate and you're looking for something to fill, that might be something you could consider.
What's the debate on, by the way, Jim?
I'm sorry?
What's the debate on? What is the title of it?
The debate was going to be on, well, you can talk to it, Dale.
Well, should we prioritize colonizing Mars?
Not prioritizing, sending man to Mars, I believe was the...
Different of the debate participants looked at the topic somewhat differently.
Yeah.
But Jim, my comment would be, I appreciate your offer and I might take you up on it, but let's talk about it offline.
Yeah, okay, I'm just tossing that out, because I understand your situation now. If we don't do the debate, then you've got to do something. So.
Yeah.
Well, again, yeah, all right.
And again, I would really suggest that doing a debate with a virtual screen would be bad enough, but doing it with a telephone as one of the slides would be extremely difficult, I would think.
Who are the participants in the debate, Jim?
Well, Bill Beers was one, but he, it turns out, is not available at that time. And Dave Bailey was another, along with Jim.
I would love to get in on it if I could, but if not, it's okay too.
Okay.
What did you say that debate is about?
Colonizing Mars, pros and cons.
Oh, that sounds great. I'll get out my moderator shirt.
Should we do it now or later?
Which side?
Which view would you want to take on colonizing Mars, pro or con?
No.
Okay.
That's my answer. I think that it's not very smart. That's all.
Okay.
Okay.
Let me consider some ths that I don't want to get into
Whatever you
here.
decide is fine with me. I don't care. I'll listen or do whatever. It doesn't make any difference. But I have some attitudes about it. But that's me. That's all. You know me. You don't have to. I don't have to explain that.
What? Ken has an opinion about something?
Maybe he has some Martian DNA.
I find that hard to believe, Kenny.
I really
like to introduce Dave Bailey to the call. Can everybody hear me?
I can hear you.
This is Dave. Can everybody hear Dave?
Yep.
Yeah,
You know, I think the best thing to
We're hearing echoes.
I think the
but we
best
can
thing
hear.
to do right now is you guys could talk about Mars right now.
Yeah, really, the question is, do you favor it or don't you favor? I mean, it's more of an emotional thing rather than a technical thing.
Not really.
Yeah, it is.
Oh,
It's
well,
not
I
an
think it's
emotional
technical.
thing. It's common sense.
Sure it is.
Dave has a lot of technical reasons to not go to Mars right now.
Or abandon exploration completely. That's essentially the argument. I mean, you can say how difficult it will be. That's another question.
That's
Obviously, it's going to be very difficult. And you can say, should we spend the money? That's another question. But whether we should or we shouldn't is a personal choice, in my opinion.
well. My thought.
My version is a two-stage thing. You do something else first, and then you go to Mars.
Well, that's fine.
And doing the first thing first will help you greatly going to Mars.
Absolutely. I wouldn't argue with you there. You're going to have to we have to do other things first before we go. That we can't. So without putting some other conditions around it, the question or the debate, if you will, of whether we should or we shouldn't is simply a matter of saying we should or we shouldn't. I suggest that we should. No, we should. We must at some point.
Well,
With today's
we preliminary thing,
10 years, which is a lot of people with billions of dollars want to go in the next 10 to 20 years, which to me seems like just a way to kill people.
Well, I don't think we can go in 10 years. But I want to do something else first, which has a minor side effect, which is that it saves the Earth from destruction. I think saving the Earth from destruction might be approved if we can talk the Congress into saying, hey, it'll make it cheaper for us to go to Mars if we save the Earth from destruction first.
That's
Well,
an interesting take.
That's
Is,
a,
does
that's a whole.
technology exist today to take someone to Mars and bring them back?
Yeah, I mean that.
I don't know. I don't know whether that's true or not. I think the answer is no, because if he said, yeah, but he's got to get there within a week from today, then I'll say, no, we do not have the technology because he can't, if he could go faster than light, yeah, we could go there and be back several times by next Tuesday.
Right.
You want to break the laws of physics? I'll go.
You're going to protect them from radiation along the way?
We're going back to the original debate that we had 4 or 5 years ago. I mean, that's another story.
Let's just show that one again.
Okay.
I'm sure we all would love.
I'm not sure I was there.
I wasn't there. I'm sure of that.
I'd be interested in to hear how many people are pro or con about it. Take a vote at one of the meetings. That'd be kind of interesting.
Well, first you got to state what
good.
it is that you're for or against. If it's in colonizing Mars is one thing. Sending people there just as a scientific expedition, that's another thing. Doing it within 10 years is another thing, or 20 years is another thing. I mean,
that's right.
They all have different answers.
You're right, Jim.
And going to Mars.
I think it's good to take a straw poll.
I don't think
if your straw poll is unanimous, then we don't have to do the debate.
Mark Wahlberg already did this. He grew potatoes. I saw the movie.
I don't think
exactly. There you go. You saw the movie. There you go.
Let's just send potatoes to Mars.
If we go, make sure you take plenty of potatoes.
You're right, Dave. If Jim's the only one for it, we don't need to have a debate.
Right.
Well, I'm taking pizza. And by the way, I'm probably not coming back if I'm going.
Well,
so
go to the moon. You can take you got a lot of cheese up there, so I guess.
No, that would be the moon. That would be that 2-step.
That's what I'm saying.
Go to the moon, get some cheese, then you go to Mars and you eat it all. Die. I think that's what happens.
We're supposed to be back on the moon in like 4 years now. So, and next week, you didn't mention that in what's in the news, by the way, Ken, that next week we will be sending the first 2 guys up to the space station on an American team.
Right. That's a big one.
That's a big news.
That would not be in the news. That's not past. That's future. So somebody else does that when it gets passed. In the news.
Good point, Ken.
Hi,
good point.
Cheryl.
Right.
In the news is about what went on since the last meeting, and whoever does it in the news next time when we do it, that's their job. That take care of that.
Good point, Ken.
Okay.
I think it's something that everybody should be paying attention to, though. I think that's next Wednesday that this is happening.
Very cool, and it's great, but that would be taking away from the next person's report, and I have no intention of doing that.
So they would be too late to watch it then.
Well, again, okay, okay.
Hey, Jonathan, are you on there right now?
Jonathan?
No.
No.
I was just wondering how many YouTubers we have online tonight.
26.
I am. I was just muted.
How many, Doug? Okay.
Since there's a little break,
I'll tell you the one thing.
I see 13. So it looks like we're at 39 total watching right now.
Yep.
David, go ahead.
Yeah, since there's a little break in the action, I thought I would remind everybody that 2 of the longtime older members of the Warren Astronomical Society, Rick Hill and Dolores Hill, have been active in Tucson for a long, long time. Rick spent many years working on the Burrell-Schmidt telescope up here at Kitt Peak National Observatory. Dolores is now the public information person for the mission that's right now orbiting asteroid Bennu and about to land and pick up a sample and take it back. And so the two of them have been doing very well, and they wish to send their regards to all of you.
Great. That's super. I'm an alumnus
Rick and
of
Dolores.
Arizona, so
Yeah, that's the
David, did
Osiris
you-
Rex mission, as Wendy just reminded me.
David, did you go to the Texas Star Party this year?
No Texas Star Party this year. It's been canceled.
Oh, is that right?
So is our annual Adirondack Astronomy Retreat. That has been canceled also this year.
Yeah. So those of you, I was talking about being at Lake Hudson. I'll see if I can show my results. That was one of the images that I took.
cool.
It got beautiful there. Now I was using a tracking mount, so I was able that's a 45-second.
I'm gonna grab a drink. I'll be right back.
Beautiful picture.
That's
that was
fantastic.
a 45-second image using a 28mm lens and on a Canon 6D. I was happy with some of the detail I was getting there.
Nice.
Yep, very nice.
And that's for Doug watching. That's after you hung up your WebEx, Doug. That's some of what started happening as the skies cleared up. Yeah, that's about when I think that's when I took that photo. Yeah, 2:26 in the morning was when I took that photo, and I was there for another hour and a half. I even took a
Stunning.
shot at the Veil Nebula just using a camera, an f2.8 camera, and I have a little star drag, and I got a satellite, but I did capture the entire Veil and this NGC object over here. I obviously have to fix my polar alignment and tracking. I don't even know if you guys see that, but yeah, no finder scope or anything. I just aimed in the general direction of where I thought the Veil was, and I caught it. That was with an infrared camera, so I got a little, I got a little more of those, some of the parts of the Veil there. So I was pretty happy with it was about a 3 or something hour night. I was happy I waited out the clouds.
Welcome to the world of astrophotography, Adrian.
Thanks.
That's just the beginning. A year from now, you're going to have all kinds of expensive equipment. You're going to get frustrated like the rest of us. You're going to say, why did I ever do this?
I know I'm heading in that direction. It's a little scary because the hit on my pocketbook's not going to be happy. I've already spent a bunch of money on photography equipment just to do regular birding. So this makes it worse. I keep looking at Doug and I go, do I really want to hit that ceiling or not? And then if Doug upgrades, the question will be, do I really want to buy Doug's old equipment or not? Doug will say, yeah, you should buy it.
One of the things you got to line up. One of the things you got to line up before you get into astrophotography is a good bankruptcy attorney.
Yeah. That's right.
Yeah.
Do I hear? Hey, Adrian, do I hear bids coming out? I do want to get that 350. You know.
Have a low mount. One of our lowbrow members, John Coslin, who unfortunately passed away, maybe fortunately before all the COVID-19 stuff started. But he passed away. I had already bought his mount and telescope to start doing observing, and I've hitched a camera on it. So I've already gone, I think, $5,000. If I count all the stuff I've bought, I've already gone $5,000 into this wonderful hobby. So
you haven't seen anything yet.
I was and yeah, I've seen what excellent equipment such as yours can pull out and how easy it can do it. The question is, will there be time, and do I want to retire now or save some money and stop buying food for a couple of years, figure out how I'm going to afford all this stuff.
That
as
is,
you saw from my photos, I need better polar alignment. So I know there's about a $200 gadget that could help me. So there's that.
It's a money pit.
Yeah.
that is indeed the astronomer's dilemma.
I could have bought a couple real nice eyepieces and stayed observational with it, but
Oh, yeah.
Pictures are the ones, especially when you see a little more than your eyes can see on their own. But I also do like having the photons of those same objects hit my eyes directly. And there's something to that. So there's benefits for both. I straddle the fence all the time.
Well, I can tell you, Adrian, the benefit is after all the money and all the frustration, when you finally get that great image that you can show that you did, it's really gratifying. It's all worth it.
Yeah, I'm trying, as you can tell, I'm trying to up my Milky Way shot game because I think I'm getting a little closer to getting a really nice shot. I have to figure out, I have the mount tracking, but I have to get my foregrounds better or figure out whether I'd rather stack images or try and take, how many seconds do I do of an exposure, all this fun stuff that I get to play around with now with this mount. So I'll be doing that this summer, practicing safe physical distancing, of course. So that's what I'm looking forward to.
Good.
All right. Well, on that positive note, let's bring the meeting back to order for our feature presentation of the night. I traditionally hand things over to Dr. Dale Parton, our first vice president at this point. Dale, you ready to take the baton?
Sure.
Excellent.
Well, I think those of us who have been in the club for a while know what to expect from Dave Bailey. But for those who are kind of new, a little background. Dave has been an astronomer in a sense since birth. Both of his parents were professional astronomers at Yerkes Observatory near Chicago. At the time Dave was born, so he grew up eating, drinking, and sleeping astronomy. Was probably taken to the observatory with his parents at night at times. If I recall correctly, he was educated at Harvard. He's been a member of the Warren Astronomical Society for many years, often referred to as our resident Einstein because he likes to give presentations with lots of physics in it. His preference, his preferred venue, is to give his presentations in a classroom at Macomb Community College, where there's a whiteboard to work on and where he can discuss things and debate things with people. And he'll have a voluminous paper handout that he gives, which he usually gets about 1/4 to 1/3 of the way through. Tonight, we're going to show his handout on the screen while he's talking over the telephone. He doesn't have internet connectivity. So this is the first time he's done it this way. Let's hope it all works well. And Dave, take it away.
Hi, if you can hear me.
We do.
Good. Okay, first page, it says the top, where is extraterrestrial life likely to be found? And there's these two professors out of University of Washington who say that complex life is not common in the galaxy. Simple life may be very common. Makes a difference. And complex life means things like humans and oak trees. And intelligent life means, quote, able to build radio telescopes. And my comment is, so Einstein and Newton were neither of them intelligent because they didn't have the technology to build radio telescopes. These two professors think that...
Focus. Got it? There we go. Right?
That's good.
Okay, we're good to go. Go ahead.
Okay, we're good to go. So, various people have had ideas that crystals might be involved somehow in formation of life, and I really like that idea because crystals can both grow and reproduce all by themselves without any life assistance, without any organic chemistry. They can both grow and reproduce. They grow by getting bigger, longer, for example, and they reproduce by breaking into pieces. Now you have the same crystal, same information stored in the crystal, but lots of little crystals instead of one big, long one. And so I really like that. And it would be a combination of RNA and crystals. The information is stored on the crystal in the form of dislocations. It's not a perfect crystal. And if you got 4 different kinds of dislocations, well, it's like the 4 different letters in RNA. And then now you've got crystals and RNA functioning cooperatively. No DNA required. Now you develop proteins, and then finally you get around to making DNA, which is the hard part. DNA is just not an obvious thing to do. So I'm going to go to another page. Here's my main thesis. Most civilization-bearing solar systems will include at least one orange or red dwarf. It's K or M.
Scroll down a little bit more, Ken.
Now,
There we go. I'm back.
Yeah. I'm going to get on the wrong page accidentally, but that's okay. I'll just keep
What
on going.
page you want, up or down?
This is the right one.
I'm going to go to
page 3.
I'm going to go to another page.
Page
So
3
we're
or
running out
page
of time.
4?
Page 3.
Okay, here's some things that we're not going to be talking about. Now, I might want to do them later. That is not today. How to search for particular star-planet systems likely to harbor life. Actually, I'm already started to work on that. Basically, you look in the plane of the galaxy. We happen to be exactly in the plane of the galaxy within way less than a part per thousand.
Dave, what page are you on?
And that's cool. I'm on page 4, but anyway, I'm not on the version that you're using anyway. I don't believe. So I'll just read. And next item, we're not going to be covered. How to listen for radio transmissions from the galaxy. You already know how to do that anyway. How to establish good communications one way, at least at first. We'll be able to hear them long before they can hear us. And we have to learn how to decode what they've got for us. Next item, how to search for aliens who might have arrived here in our solar system. And that's a plot element in my sci-fi story, which I'm currently writing. And there's several possibilities there. There might be aliens that have arrived in the asteroid belt and have set up a colony. That's really stupid, in my opinion. If they're going to set up a colony, they should at least tell us they're here. Now, admittedly, in my sci-fi story, that's not the way it plays out. But it's more fun if people don't know what's going on. Next, how to build a low-tech, realistic starship, not faster than light, nowhere near the speed of light. There's another one of the items I'm not going to talk about today. Low-tech does include nuclear power, fission, and/or fusion for the benefit of the ship and for the benefit of the inhabitants. To launch such a starship is still in stuff that I'm not going to cover. The launch alone would probably take several hundred years. And safety is essential because this is a medium-sized starship, and a big error could cause a KT-type extinction. If you crash the thing into Earth at full velocity, you'll kill off all the dinosaurs that might be left over, and maybe us too. How to live in such a starship many thousands of years after launch, because this is not us. Can't go anywhere near the speed of light, and so on. Skipping over a bunch of that stuff. Now, let's go back to real life here, what we should be doing. Let's short circuit the entire Drake equation just to save time. I got tired of the Drake equation for a long time. Here's my short circuit of it. How many stars are there in our entire galaxy? And a lot of people say about 250 billion. Okay, fine. I wrote that down. How many civilizations do we know about? Well, just one, which is our own. And let's go halfway between those two numbers, ratio-wise. So you multiply 1 times 250 billion and take the square root, and you get 500,000. That's an excellent number. If we guess that there are 500,000 civilizations in the galaxy, we could be in error by at most a factor of 500,000, one way or the other. That's the square root of 250 billion. Exactly. So now we know there's 500,000 bunch of aliens out there in our galaxy. So that's my estimate of how many races of ETs there are. Wasn't that easy and quick? We didn't have to go through the whole problem of going through all the numbers of the Drake equation. Some would say 500,000 inhabited solar systems is a huge number. I'm pausing just to let that sink in. 500,000, 500,000 in our galaxy? But that number is also a tiny number because for each star which is providing light, warmth, and sunburn for a race of aliens, there are 499,999 lonesome stars which don't have anybody to give sunburn to. Hard to believe, but true. The Milky Way is that empty. So this huge number is a tiny number. Maybe it's a good procedure to come up with a number that seems to be both huge and tiny. On the page. There's some issues which concern Ward and Brownlee, who are the authors of this book I'm working from. Here's trouble. I'll list trouble things and solution things. Trouble. A planet with rotation tidally locked to its star. The solution is lock it to something else. And the example I have to mention is the sun, the earth, and the moon. The moon might get tide locked to the star, but we will preempt that. We will tide lock our moon to our earth. And that's what's actually happened. So I'm saying the alien populations out there mainly live on their moon. They do not live on their earth. An alternative, which actually has water, is Europa, Jupiter, and the sun. Europa is tide-locked to Jupiter, which means that it cannot get tide-locked to the sun. That's good. Next, a star with a short main sequence lifespan is the problem. Solution is use a lower mass star. Low mass stars live forever. K dwarfs, M dwarfs. Whereas our Earth has already used up most of the time that it's got. The sun will start to become a red giant soon. So the sun is way too massive. They evolve much too fast. Problem, too much ultraviolet light. Solution, use a cooler star. There's no reason for going to a K or an M dwarf. Much, much less ultraviolet. And some of those stars are flare stars. While they're flaring, they do produce ultraviolet. So there's no perfect solution. A variable star. Well, we can talk about that later if we can get to it. A moon which is too small. Okay? Trade it in for a more massive moon. Our own own moon on the Earth is massive enough so that it stabilizes the Earth. Take Mars for an example. Mars doesn't have a massive moon. And according to the celestial mechanics, things in the solar system, like the gravity of Jupiter and Saturn, can provide small torques to planet Mars, which can tip Mars over on its side. Mars supposedly can vary over a period of millions of years or so. They vary from almost a tilt of 0, like Mercury, a tilt of 0, up to a tilt of 85 degrees. Well, gee, that's a major thing. And if it happens slowly enough, there's no problem. If it happens quickly, then it could be a major problem. It could cause a major extinction. Asteroid impacts. For asteroid impacts problems, you want to get a larger Jupiter. In fact, Jupiter, Saturn, Neptune, and Uranus, all 4 of them protect us from asteroid and comet impacts. How do they do that? Well, just big targets out there. Jupiter, for example, is like 100 times the area of the Earth. It's a big target. Plus, its escape velocity is large, so it can actually suck in, with its gravity, suck in objects which otherwise would have missed the target. And, well, like Shoemaker-Levy 9, for example. I don't know what the current idea about what Shoemaker-Levy would have done if it had hit the Earth, but I don't think I'd want to be anywhere near when that happened. Troublesome Jupiter, another problem. Jupiter's often, in the early stages of development of a solar system, they spiral inwards. How do they spiral inwards? Well, they're going through a medium that's fairly dense. It's got a lot of asteroids in it that crash into Jupiter. I mean, it's more than just Shoemaker-Levy 9. It might be dozens of asteroids every day hitting Jupiter. I don't know. I've done the math about that one. So Jupiter gradually spirals inwards because it's going through this dense material, which is mostly empty space, but does have, things like asteroids in it, and also gas. New stars tend to produce a lot of gas, humongous solar wind. So this troublesome Jupiter gradually spirals inwards. And as it goes inwards, its gravity takes Mars and makes Mars spiral inwards, and the Earth spirals inwards, and Venus and Mercury spiral inwards, and everything spirals inwards. Okay, we've just destroyed all the terrestrial planets. That does not feel bad. Well, no, because Jupiter also spirals in and goes into the sun. The sun's happy. It's got a lot more mass. And a new Jupiter forms out there. And it is said that in many cases, according to the computers, several Jupiters form, spiral into the center in a solar system and crash into the sun. Eventually, a Jupiter forms. It starts to spiral in, but just about that time, it runs out of stuff to hit. That's our present Jupiter. And our present Earth doesn't get spiraled in and destroyed. So, yeah, if you got a large Jupiter plus Saturn plus Uranus and Neptune, and I've got numbers to look at that there, then that's good. Snowball Earth episodes. If things don't go perfect with the Earth, then the whole planet can have a global ice age. And according to a lot of the people who studied this, once you get stuck in a global ice age, you can never get out of it. You won't get out of it until the sun goes red giant. And we don't want to wait that long. So that's a problem. And the solution for it, I and also the authors say, use larger oceans in the tropical latitudes. And by the way, I talk as if I'm designing and building the solar system. And yeah, I can design them. I can't actually build them, but so many of them are being formed out there. Whatever I say as a design feature will be incorporated into some of those solar systems out there that are forming right now as we speak. Let's see, next item, unreliable plate tectonics. And the solution is pray, because I've been pretty much convinced by these two authors that if the platonic system stops, it would probably never, ever restart again. And then we'd be in big trouble. We'd probably go extinct fairly, well, not instantly, but eventually. And it goes on and on. chemical abundances which differ from our own Earth. That's not too bad. An Earth which is larger or smaller than our own Earth, that's not so bad. I'm going to go to another page. Too small a moon, we already mentioned that. Keep going. After impacts, we did that. Okay. I'm going to go to a list which may not be visible to you because it's small print. That was supposed to be originally in the paper handout.
So we're so right now the moon has spiraled out very rapidly at first. Should we move
I
beyond
didn't
that?
hear what you said. Where are you at?
We're at the moon spiraled out very rapidly at first, which is the bottom of page 8
okay.
for us.
Yeah, we can do that. That's cool. That's cool. Formation of the moon. If I can find it. No, I'm not finding it. Anyway, what you want to do, you want to concentrate on red dwarfs and orange dwarfs. And you got two huge advantages. One is there's billions of them, way more than G-type stars. And the other is that they last forever. And like our current age of the universe is 13.8 billion years. A lot of these objects have lifespans of like 100 times that order of magnitude. And it really doesn't matter that much because we've only been in existence for like 10 billion years. Well, we got a star, which is good for 10 billion years if you include the subgiant stage. But that only gets you to what, somewhere between 10 and 20 billion years. And we're talking, with these red dwarfs, we're talking 100 billion years. Something like that.
Dave, you're fading sometimes. Please talk right into the phone. And what page are you on?
Oh, on page 16. But this is a follow-on thing I'm on right now, and let's see what we got here. We're skipping over a bunch of stuff. Okay. What about Jupiter? Talking about brown dwarfs. Talking about naming the stars. An anecdote which you're not interested in right now. In a way, we humans do live on a rare Earth because we orbit around a rare star, which is the sun. The sun exceeds the great majority of stars in both mass and luminosity. In percentile terms, the sun is at the 92nd percentile and the 94th percentile in mass and luminosity. Our sun is certainly not a typical star, in spite of what many basic astronomy texts say. And then I ask the question, what is a typical star? And I come up to the answer which I've already given you, which is K dwarfs and M dwarfs are really our typical stars. Let me go through some numbers there.
It looks like 12 is the page that we're at.
Star. What?
I think page 12 is the page that we're on, and if you scroll up a little bit. Maybe 11.
I'm on page 20 right now, but this
right.
is not relevant.
We're not,
and
we have 40 people looking at this screen, so the page that we're showing on this screen is the one that matters the most. So, Ken, can you scroll up a little bit more?
What do you want me to do? Or are you saying what I want you to do?
No, sorry, I'm telling Ken to scroll up a little bit. No, it looks like we got past that. So
anyway,
so are we past the table? Dave, are we past the table of useful stars and planets?
Yeah.
Okay, so go down to page 20, Ken.
Yeah, maybe 20. The largest print on it, the darkest print on it says, "What is a typical star?"
Yep, that's it. So it is page 20 for us.
Okay, cool. Yep. I'm in the bottom of that page of the right column. I'm talking about a typical star, and what is it? It's a L726-8A. Its spectral type is M5, and its luminosity is 0.011 times as bright as our sun. So it would take 91 of these stars to equal the sun in light output, including the infrared, of course. And it's mostly infrared because we're in the M5 region. But first, let's take a look at it. Its surface brightness is only about 8% of the sun, but that's still 8%. Oh, yeah, the surface brightness, yeah. You still don't want to look at it. You don't want to stare at it if it's only as bright as 8% of the sun, because it's still about as bright as the filament of a tungsten light bulb. You will need very dark glasses, and I'm on the next page, 21. You need very dark glasses, and I wouldn't look for more than 1 second if I were you. Most of the light is infrared, and this is important. Most of the light is infrared, so it's much brighter than it looks. And that warning also applies here on Earth at sunrise and sunset. The infrared can damage your eyes, so don't stare at the sun, even at sunrise or sunset. And next, a typical planet. Suppose we wanted to live on a planet with a comfortable climate orbiting that typical M5 red dwarf. Exactly where does that planet orbit? Well, we just take the square root of 0.011 and we get a simul major axis of 0.105 astronomical unit. For comparison, our own Mercury orbits quite a bit farther out at 0.387 instead of 0.105. If that star, that L725-8A, if that should turn out to have a planet at 0.105 AU, then that planet would have an average temperature similar to our Earth, but there's a catch. It's just too close to its star. This candidate planet would get tide-locked for sure. If you traveled there in a space expedition, you would probably think its front side was a bit too hot and dry, about 242 degrees Fahrenheit at the subsolar point, according to my rough mental calculation. When you went searching for its water, you would find all the water on the planet's cold backside in the form of a gigantic ice cap, an entire Pacific Ocean, almost entirely frozen, perhaps 15,000 feet thick. And that's not good. Way too hot and dry on one side and way too frozen on the other side. So you don't want to get any star tide-locked. I mentioned this twice because it's important. Okay. The professors, Ward and Brownlee, that's their names, out in Seattle. They think that that's a big problem. The tide lock is enough of a nuisance to eliminate all red dwarfs from consideration as host stars for life. However, I take almost exactly the opposite position. I like those low-mass stars. They're useful objects because they can cause nearby planets to become tide-locked in a harmless way. You have a binary system, which is one star, which is maybe, a K0 star, something like that. And the other star, that provides light and heat. And I call it the light and heat star, actually. And you have a second companion star, which is maybe an M5, which is very dim, doesn't provide much light, and you let the Earth become tide-locked to the harmless one. In fact, I call that secondary star the tide-lock star. And as I said already, we got that situation with the Earth, the Moon, and the Sun. The Sun is the heat and light star for anybody who's living on the Moon, and the Earth is the tide-lock star for somebody who's living on the Moon. And you want your tide-lock star to be not very bright. Well, the Earth isn't very bright. It's so bright, it's so dim that it doesn't even count as a star, but it does get the Moon tide-locked to it. So it's good. And then I talk a bit about living forever, the star living forever. M5 through M7 stars is what I liked when I was writing that page. I'm now not looking for stars that are quite that dim. I'm going to go down a few more pages. Little comments about terraforming. Supposing we wanted to terraform the Earth or the Moon or whatever, any object that was worth terraforming. Supposing we wanted to do it for 1 billion years. And that means that you got to make our society totally sane because of the kind of technology we would have as we go out through the millions of years. We get so powerful that we could destroy the entire Earth in less than 1 year. Like one major war would do it. So we have to achieve this situation where the chance of a major war occurring next year must be less than 0.000000001. That's one chance in 1 billion. If we do not achieve that level of societal sanity, we will not have achieved billion-year terraforming. How will we know that we have achieved sanity? We will have to wait and see. If we go for 1 billion years without producing one person as insane and as influential as Adolf Hitler, then we have succeeded. If you get one person that insane and within the 1 billion years, then we've failed. So the point I'm making there basically is there's all kinds of terraforming. One is in terraforming for like 1,000 years. We have not achieved that in the case of the Earth. It's not clear whether the Earth will survive for 1,000 years. It might not even survive 100 years, just because of global warming and species destruction. We'll make our own mass extinction if we're not careful. So here's a quick overview of the main sequence. I'm still on page 23, it looks like. There's 3 things that I like to look at on the main sequence chart. The luminosity, L, the mass, M, and the ratio of the two, which is M divided by L, and we'll use solar units. So the sun has L equals 1, M equals 1, ratio of the two is M over L. And that ratio tells you how long the star will stay on the main sequence. And in the case of the sun, you divide L equals 1 by M equals 1, and you end up with L over M equals 1 also. And we happen to know, in the case of the sun, the celestial mechanics people tell us that the sun is good for 10 million years, maybe 11 million, billion. 10 billion years, maybe 11 billion years. And the majority of that time is actually not technically on the main sequence. It's as the sun is gradually creeping away from the main sequence and becoming a subgiant star. And I think with the kind of experience we would get in another billion years or so, we should be able to adjust the Earth so that we can survive for longer than we would have thought. So the lifespan of the sun in the main sequence I've set to 11.8 billion years. And that's the most optimistic idea that I got out of my serious astronomy books. And that includes the early part of the subgiant stage as well as just the strictly speaking main sequence. But if we don't want to use the sun when we create this, life system out there somewhere, we pick a smaller, dimmer star. And I've mentioned this already. You buy yourself a whole lot of time, huge amounts of time. Let me go to the next page.
Dave, you're drifting away from the microphone again.
Yeah, I know. I'm trying to find a button on my phone. I was getting ahead of myself by talking, not rolling. Come on, guys. Now it's working. Yeah. All right. Next question. Can planets form in a binary star system? Good question. I've heard that question asked numerous times. Well, we can answer them. Just count the number of large moons in our own solar system. Our solar system is, of course, a binary of the Sun and Jupiter. I count 14 large moons. That is about the size of the moon and bigger. And those moons orbit around Jupiter, Saturn, Earth, Uranus. And they all get tide locked, every single one of them. So it's working. Our tide lock star, unquote, which was the Mars and the Jupiter and the Saturn and the Uranus, they are tide locking them, which is what they're supposed to do. And those are the tide lock stars. The heat and light stars are the sun. So it does work. And we also know what I was setting out to prove, that moons, we're calling them planets, but they're sure the sun called moons. They can form in a binary star system. I mean, look at Saturn. Saturn's got a dozen of them.
Could you speak closer to the microphone again? Yes.
You're hearing me?
We are now.
Okay, good. So the fact that moons form around massive planets in our solar system means that planets can form in a different solar system, even though it is technically a binary. That's good to know. I'm going to go to another page. I hope I'm going fast enough. How slowly can a planet rotate and still be habitable? Now, our professors, Ward and Brownlee, might say 24 hours is the limit. If we slowed down to 25 hours, we'd all go extinct. I'm not that much of a pessimist. The Earth's moon clearly rotates too slowly for life at present, because it's not, it's tide locked to the Earth, and so it rotates way too slow. But if it had a deep enough ocean, it could harbor life. You could have life on the moon. If you could put an ocean there and keep the ocean there and not let it, escape into space. How deep is a deep enough ocean? I would guess 100 meters might be enough, but 1,000 meters would certainly be enough. So, yeah, we could have life on the moon, in the ocean. Probably not on dry land, because if it's only going around once a month, I think dry land would be very unpleasant. With modern technology, you might be able to survive. And I mean, the Apollo people didn't die over the heat there, but they knew what they were getting into, and they had relatively high tech to deal with it. If you just turn somebody loose on the moon with a good atmosphere and no water, I think they'd die from the heat. Because, half a month of heating with the sun right overhead. So
sometimes I think I'll die during the summertime in Michigan with plenty of moisture.
Yeah. Talk a little bit white dwarfs. Take a look at the white dwarfs. Oh, I didn't make a point. I started to talk about Sirius A and Sirius B, which is a white dwarf. And my initial pass through it was, yeah, it'd be interesting if there could be life on Sirius. But where would it have to be? It couldn't be orbiting Sirius A. Because, you could put it out in a safe distance so that it doesn't get scorched. And that's fine for 50 years. But then here comes Sirius B. It's on a 50-year orbit, and it comes around, and its gravity grabs your planet and slings it out of its orbit, which you carefully placed it in to be, healthy place to be at the right distance from Sirius A. You could, on the other hand, orbit your planet around Sirius B. Now, actually, you can't because Sirius B is a white dwarf, and it went through a red dwarf giant stage before it came a white dwarf. And when a star becomes a red giant, it totally wipes out all of the nearby planets. So that won't work. But then I said, hey, wait a minute, we got another option. We could have a starship from some other star system orbiting Sirius B. That would fly. I said, holy cow. And this is totally irrelevant for what this presentation is about, but it reminds us of the fact that you could have in a solar system, which is a total disaster, like Sirius, you could have somebody there living. How'd they get there? They got there in a starship. They just parked. And they could be parked for millions, 100 million years. That's okay, provided they've got enough uranium and plutonium. You got to be parked there for a long time. So it's another case of finding aliens unexpectedly, where you didn't expect to find them. As, for example, in the asteroid belt, which I already mentioned. Like a starship arrives at the solar system, and they decided, well, we'll just set up a colony in the asteroid belt, and we won't tell anybody we're here, which is totally unrealistic. But first thing they do is tell us they're here. But they could also be orbiting Sirius B. Okay, so we got to have an open mind about things that are widely understood to be impossible. Let's continue. Yeah, red dwarfs. All right. So the bottom line about the Sirius is just because you got a starship doesn't mean you can go everywhere. And the Sirius case is one where there is no place you can orbit either the Sirius A or the white dwarf. White dwarf is nasty because the light from it is strong and ultraviolet. It's really strong ultraviolet. And the best example I could use to compare it to is the fireball from a nuclear bomb. That's what Sirius B looks like if you're close enough so that it could actually keep your spaceship warm. And so it's just a tiny speck in your sky, but it's got the amount of UV as a nuclear bomb explosion. You don't want to. What kind of paint do you use to paint your spacecraft? You'll have to repaint it every year. And I'm not going out there with a paintbrush in that kind of ultraviolet. So the bottom line is there really are places where you can't go in a spacecraft, and white dwarf stars are among them. So back to red dwarf stars. I'm on page 28. On my list of stars and planets, which is way back on page 3, but we skipped over, just by coincidence, I seem to have listed 24 stars and 24 planets, and moons, of course. Some of these objects will be more useful than others, so we will do some eliminations and make some rules. The A column refers to the heat and light stars. The B column refers to the tide-locked stars, or planets. C refers to the, quote, habitable planet candidate, which is all those moons, basically, in the case of our solar system. And then it talks about how do you assemble a sun, earth, moon combination. Basically, you take one from column A, one from column B, one from column C. Column C is the, quote, moon. Well, quote, the quote, moon, but we're calling it a planet because everybody lives there. And in a place that cannot be tide locked to the sun because it's already tide locked to the earth. So it's okay. And so I talked about that for a little bit, and I mentioned some possible combinations. And one of the combinations is, here's the count of column A has 13 objects listed. Column B has 20 objects listed. Column C has 10 objects listed. So pick one from each column and see if they will work. Here's a big one, because they are going to vary in size. We'll pick the sun from column A. From column B, we'll pick Groombridge 1618, which is an M0 dwarf. And column C is the Earth. So the Earth is orbiting around this dim M0 dwarf. And this M0 dwarf in turn orbits the sun-like star, which in this case actually is the sun. Okay, so that's what a big combination of sun, Earth, moon looks like. Here's a small one. Column A, Wolf 630c. Column B is Venus, and column C is Europa. So Europa is tide-locked to Venus, which in turn orbits the M7 dwarf, Wolf 630c. Here the primary star is extremely dim. This system could be quite close to our own solar system and go undetected. Suppose by unlucky chance that it was aligned perfectly with the glob M13 in our sky, or maybe M15. We might never see it.
10-minute warning, Dave.
And,
10-minute warning.
What did you say?
10-minute warning.
Cool. Yes, I heard that. It's a mid-sized one. The light and heat star is Kruger 60A, and the tide lock one is RG 0050, which is a brown dwarf, and the star that people live on, the planet that people live on, is Titan. So Titan is tight-locked to the M8 brown dwarf, RG 0050, which in turn orbits the M3 dwarf, Kruger 60A. I'm going to continue on the next page. Another constraint which should be obvious, the AD orbit, that is the orbit of the Earth, and one we're accustomed to, the AD orbit must be much larger than the BC orbit, which is the orbit of the Moon, orbiting around Earth. If the orbits are too close in size, the gravity of A might pull C away from B. In that case, the Moon would get pulled away from the Earth, which will eventually happen in the case of our solar system, but we hope it won't happen for a long, long time. Okay, here's another issue. The AD orbit, which in our case is the orbit of the Earth orbiting the Sun. Habitable planets want to be distant from their stars so they don't scorch. They also want a circular orbit so that their seasonal climate contrast is minimized. Unfortunately, in the case of stellar binary orbits, these requirements tend to be contradictory. Round orbits tend to be very tight, and large orbits tend to be rather eccentric. Okay, so basically, you abandon the classic binaries. And you look at the binaries, which consist of, say, the Earth and Jupiter, and you live, say, on Callisto. Or you look at the Earth and Saturn, and you live on Titan. Those seem like the more practical ones to use, types to use. Talk a little bit about the entropic principle. Let me see, how do I introduce this? Oh, yeah. I assume that there's some significant difference between how stars form in binary systems versus how planets form in a solar system. That unknown difference would explain the differences in the resulting orbits. I mean, the things orbiting Jupiter are in circular orbits, and Jupiter orbits around the sun in a circular orbit. That's good. All that is good. But there's another possibility, namely that almost all solar systems form with crazy, chaotic planetary orbits, and the resulting crazy, chaotic planets either never form in the first place, never form life, and certainly never form intelligent life. That would explain why our own solar system is orderly and not crazy. We can only live in an orderly environment. There's a name for this idea. It is called the entropic principle. It's often applied to the universe as a whole. And the idea, which is invented by a philosopher, not an astronomer, is that there may be entire universes out there somewhere in which everything is chaotic. The laws of physics there don't make any sense. Of course, we could not possibly live there because anything as complex as a human being requires an orderly environment. So we live in this universe where the laws do make sense. There are, of course, scientists who point to the apparent contradictions between quantum theory and pretty much the rest of science, and they say, look, the laws of physics here don't make any sense. We do live in one of those crazy universes. Anyway, I think the entropic principle probably does apply to the formation of stars and planets. So our own solar system, at least, must be orderly because we live here. And then I start to introduce the idea about starships being huge and slow. And just quickly, the starship that's in my sci-fi story has a population of 3,456 aliens. That's a round number in base 12. The aliens have 6 fingers on each hand. Well, they have 2 thumbs, one on the pinky finger. And so they use base 12 arithmetic. So 3,456 sounds like a good number for the crew of a starship. You need a lot of people on one of these starships because you're going to be there for many thousands of years, since they don't go anywhere near the speed of light. And I talk a little bit about why that is, so you can't go faster than the speed of light. And the answer is it's about the topology of space-time. And the truth is there are no velocities out there which are faster than light. And that seems strange, but the best image I know of to get this idea across is the airplane pilot who wants to fly to a point 60% of the way around the world. You tell him that he can only fly to the 50% point because beyond 50%, he will just be returning. But he doesn't get it. You tell him it's about the topology of a sphere. He says, don't give me that topology nonsense. When I get to 50%, I won't turn around. I'll keep on going till I get to 60. I've installed extra fuel tanks. You tell him there is no such place on Earth, but he still doesn't get it. He says, what could stop me? Is there a giant brick wall that goes up to the sky? You tell him, well, that's what some of the crew members on the ships of Columbus thought. So in this case, due to the topology of space-time, there are no velocities beyond the speed of light. But no, I'm not saying space-time is a sphere like Earth. Both of these phenomena are topological, but they are not identical. And at this point, there's a note in big print that says, material beyond this point was brought over when I did a save as. If I have time, some more of it, not all, maybe reformatted to be included in a large version. But then I did another save as, so that is not on my screen right now, but I can quickly grab it.
Dave, we can't really hear you.
Yeah?
Yeah, you're mumbling.
Yeah, and I think we've sort of
pretty much hit.
Yeah,
we've pretty much hit
You're running out of
the
time.
Yes, I have 2 minutes. So
okay, cool.
Does anybody have questions for Dave?
I do.
All right, Bill, go ahead.
Dave, what did you mean earlier in the presentation when you said that we would become extinct if we did not have plate tectonics?
Oh, all kinds of things go wrong. One thing is, without plate tectonics, you don't have mountain ranges. You're like Mars. Mars has got this humongous mountain, a number of places. Venus has this humongous mountain, but no other planet that we know of has mountain ranges. Why we have mountain ranges? Because of plate tectonics. And the other thing that plate tectonics gets us is, if I have this right, is continental shelves. And that's partly because plate tectonics was partly by dumb luck. We got just enough water in our oceans, so the fringes of all our continents are covered by shallow water. And these two, one of them is an astronomer and the other one is a geologist. And they're both planetologists. And they say, that's very, very fortunate. We just have the exact right amount of water. And we have just the exact amount of land. Our land is 1/3 of our surface area, and our oceans are 2/3 of our surface area. And they keep saying this, that the Earth is just incredibly lucky. And I keep saying, actually, the Earth has been incredibly unlucky in a number of times. And that's why it's taken us 4 billion years to come up with intelligent life.
That's the misanthropic principle.
So are we lucky or unlucky?
Yeah.
What?
Gotcha, Dave. Good.
I didn't hear that.
All right. Do we have another question? Well,
I'm convinced, by the way, we need plate tectonics. I'm convinced in that regard.
I agree with you. I very much agree with that one. All right. Well, thank you, Dave, for another journey to the edge of the solar system and beyond. And normally at this time, we would place a call for gastronomy, but since we can't go to any restaurants together, I advise you to partake of refreshments in your own house at your own time, and we will see you either at a virtual open house / discussion group or at virtual Cranbrook on the 1st of June.
Yeah.
Sounds good.
I have an announcement.
Yes, Dave.
Hello?
Yes, David.
I have an announcement, which is that once I get the expanded version of this handout, which could be 60 pages by the time I'm done, it will be available in paper copies at future meetings, if we ever have a future meeting.
I would suggest a special issue of the W.A.S as well.
Yes.
Oh, sure.
I would agree with that entirely.
Yes. All right. Thank you very much, everybody. Thanks for our special guest joining us. Thank you for everybody who shared their observing stories and other adventures. And have a good night, and we will see you.
We'll keep in touch.
Indeed. Take care.
Thank you.
David, I'll keep in touch with you. I'm going to call you tomorrow. So.
And feel free to stick around if you like.
we'll
I'd like to stick around for a minute.
keep it open for a little extra time.
Okay, we could do that. I'm good with that.
So
Anyways,
I'm still here. Anybody have observing plans? Actually, we didn't hear anything at all from the Gary Ross party. Is there anything that Clayton and Gary and the other gentleman whose name I forget would like to say? I unmuted you. I think Gary is lying supine in the sunshine.
could very well be.
Actually, we're here. I had the microphone turned off.
There you are.
Aha.
I see you.
It took me a while to figure out where the mute button was, which is why I wasn't using it. Gary is offended that he sent 3 Jupiter reports and nobody found them or read them for him.
Oh.
Oh, poor Jerry.
I thought they were for the WAS.
Yeah, we thought they were for publication.
Oh.
All right.
We'll make certain those get into the WASP.
Too late. They're not announcements, Gary. Now they're printed. They'll be out when? June 1st, did you say it's printed?
June 1st. Or the day before.
I was almost paying attention. My father would say.
That debate, Dale, could possibly go on this thing. Dale?
What?
I think the debate could actually be held on here.
I do too,
I think
although
the
it would
debate
need
would work
a lot of
okay.
structure.
Mm-hmm. Well, we could
Need
do
a strong referee.
Right.
Well, with
we have a pretty good one.
Actually, with this though, we have the ability to have a mute button. So if somebody's
right,
just mute them.
Somebody's saying you put a mute on. That's great.
Out of order, click.
I know 3, click.
Ad hominem. Argument from absurdity. Click. Do not like, do not want.
We're still live on YouTube, by the way.
Unless
you would like me to just.
So I can read Gary's report, or Gary can read Gary's report, but
why we can read the report since it was actually intended for tonight, and then splice it into the right?
No, splicing things is hard.
Okay.
I'm still
live.
YouTube doesn't give me very good tools
If you
for
wanted
that.
to splice it, that's a challenge.
Would you like me to keep the?
I could download it and splice it and then re-upload it, but it wouldn't most likely be worth.
Much awaited observed report. 8-9 May, Veen Observatory. Before dawn, I observed Jupiter with 5-inch Newtonian at approximately 100x. The planet is currently low in the Sagittarius ecliptic, but it also still down in the southeast whilst climbing. Gibbous moon was just past transit. Seeing was unexpectedly good given Jupiter's elevation. Although transparency was excellent, he was slightly yellowish, an effect of elevation plus possibly the proximity of the very bright moon. The north equatorial belt was very active and very dark knots across the disk. By contrast, the south belt was wan, without remarkable features, grayish purple. Interesting were the Galilean moons. The farthest west, L, was Callisto, the blue satellite, strikingly dim. I know of no elongation effect affecting magnitude, analogous to Iapetus in the Saturn system, so the dimming was from moonlit sky. To the east of Jupiter was a cat's eye formation, made by Io and Europa in very close conjunction. Without referring to other data, I reckon Io was at, or very near, greatest elongation. The brightness of the ball of Jupiter and the moon made it difficult to decide which satellite was which. Intrinsically, they are much different colors. Europa, the white ice world. There is another possible factor, the color vision in my right eye. Alternately, I declared one or the other, the ice world or the volcano world. Reference to the graphic presentation in the Observer's Handbook will resolve this minor mystery. Respectfully submitted, GMR, Master of the Small Aperture. Number 2, for the record, 12th May, Bean Observatory. Jupiter in conjunction with gibbous moon approximately 100 times, seeing good and planet very low. All the activity on the north equatorial belt previously reported is gone. Either the dark features are on the other side of the planet or have subsided. South equatorial belt remains unremarkable, although wider. Io is very close to south equatorial limb and faint from strong forward scatter by the moon and the planet's ball. Likewise, Jupiter himself was more washed out by moonlight from above. Also, striking triangular lunar planetary asterism, quotation marks, in Sagittarius this mid-month. And finally, from the following night, 12th and 13th of May, Bean Observatory, observe the giant planet, start of astronomical twilight, gibbous moon down to the east of the planet. Seeing fair, location in Sagittarius, a disadvantage. Indeed.
Indeed.
At approximately 100 times in long focus Newtonian, 2 interesting points. A, previously reported darkenings in the north equatorial belt have returned, approximately equal extent on both sides of the central meridian. They completely dominate the belt, no equivalent in the opposite hemisphere. B, east of the ball, Io stood close by, but much further out was a spectacular conjunction of Europa, Ganymede, Callisto, a tiny triangle pointing down. More colorimetry possible. Ganymede was distinctly creamy next to the ice moon. Callisto was small and faint in comparison to the others, probably a function of the sky turning slightly blue. Size made comparison impossible. Ganymede is the solar system's largest satellite, over 2,000 kilometers larger in diameter than Europa, and obvious. Callisto is about 440 kilometers smaller than Ganymede, but seems smaller yet, a function of color as the blue moon. Callisto is truly dark. To happen upon such an asterism makes planetary observation of interest every time a world is brought observation.
One correction, it actually said size comparison was possible.
Oh. My eyes are a bit dim at this point. But you can see how lengthy and literary that was, that I assumed it was meant for immortalization in the pages of our paper, rather than the ephemeral reading.
I just read the same thing. I agree with you completely. He should be a writer.
I have another report by the another
He's a writer.
a new thing I found on Europa. I just found.
Yes, sir.
Let me. There's a more evidence for watery plumes on Europa. It's a May 18th report. It just came out. It's saying that the huge plumes of water vapor erupting from the enormous cracks on the surface of Saturn's moon Enceladus were quickly found by the Cassini spacecraft. It also says that they're thought to have to arise from a salty global ocean in the moon's ice crust. Over the past few years, evidence is accumulating for watery plumes on Jupiter's moon Europa. It's taking longer to put the pieces to the puzzle together, but although still not definitive, the data for plumes on Europa are beginning to look more compelling. They indicate like geyser-like plumes erupting, at least occasionally. On May 12, 2020, researchers at the Max Planck Institute in Germany and the European Space Agency reported yet more evidence that, for watery plumes on Europa. The new work supports previous studies that suggested that although it wasn't recognized at the time, Galileo spacecraft glimpsed one of these plumes during a flyby in 2000. The researchers published their work in the Geophysical Research Letters in late April. Making a case for the plumes on Europa have been a long process, since from the evidence gathered so far, they are seemingly intermittent. And in contrast, the plumes of Enceladus are large and easy to see, and at least at the time were erupting continuously. So apparently there's now a study that says that we've got it. And that would be a huge thing because of the size of Europa. You know, Europa's bigger than the moon. And with that kind of, it says, use a computer simulator. Let's see if there's something else that says that. EPD is the energetic particles detector. recorded the distribution of high-energy protons trapped in Jupiter's powerful magnetic field, which is 20 times stronger than the Earth's. Europa orbits within the magnetic field. Back in 2000, the detector recorded fewer protons during the flyby than had been expected. At the time, it was thought that Europa itself was blocking the view of the detector. But now the new study suggests something else. The researchers modeled the movements of protons during the flyby in an attempt to reproduce the original result from Galileo. But surprise, they found that the only model that matched the results was one where the water vapor plume was between Europa and the detector. The plume would have disrupted both Europa's extremely thin atmosphere and the magnetic field. This also would have changed the amount and behavior of the energetic protons. When the protons collided with the uncharged particles from Europa's atmosphere or plume, they took electrons from them, become uncharged particles themselves. As Hans Heibright of the ESA, lead author of the new study, said, this means we're no longer trapped in Jupiter's magnetic field and can leave the system at high speed. Therefore, the decreased number of protons detected during the flyby would have could be explained by the water vapor plume. Last year, it was reported the water vapor itself had been directly detected above Europa's surface by researchers using the Keck Observatory, and according to NASA scientist Lucas Paganini. Essential chemical elements, carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur, and sources of energy, and the sources of energy, 2 or 3 requirements for life, are found all over the solar system.
Ken, we get it. You don't have to read the entire article.
But again, that's a very, very interesting study. I'm sorry, I got carried away. I was
yes, I know, but it's like, dude.
I got it. It's okay. You're cool. I'm good with that. I really am.
Yeah,
I got carried away. Honest to God, I did.
I've been doing Zoom meetings since 11 o'clock this morning, man.
I know. I'm sorry. I got enwrapped by the.
And on that note, everyone, I'm going to have to go.
Well, thank you so much for joining us.
Thanks so much for joining us.
I really enjoyed this evening, and thanks for inviting me to come. I'll see you next month.
I hope you see you.
Thank you.
Yes.
Okay.
Thank you.
Bye.
Yeah. Yeah, I gotta get off the computer.
Yeah, I think.
I'm sorry.
Yeah,
guys.
Diane.
Sorry.
Good night, everybody. We'll see you soon.
We're spending all day, every day on video calls these days for work. So
Zoom fatigue is real.
Oh. Yeah.
All right. Great study, by the way. All right.
Yes.
Thank you very much for tolerating my nonsense.
For doing these. I really like it.
Good night, Riyadh. Good night, everybody.
Good night.
Bye.
Good night.
Thanks for running the presentation, Ken. That was super helpful.
I appreciate letting me do it. I enjoyed doing it. It was good.